Okay guys, welcome back to another session on Laplace transformation. So our last video or last session on Laplace transformation, we treated the second theorem in Laplace transformation, which you said is multiplying by t. So now but this theorem, we're going to be treating division or dividing by t. Now the theorem says if the Laplace of a function of t is equal to the function of s, as we know, then the Laplace of a function of t divided by t is equal to the integral coming from another variable which we just introduced to infinity of a function of that variable with respect to that variable. Now that variable, how we got that variable is irrelevant. You can represent it with another letter of your choice, but you just express it in that variable and you understand why I'm expressing it in that variable. So before we proceed on how we're going to be solving questions that involve the Laplace of a function of t divided by t, let's just prove that the integral of this s, or the integral of this function of this variable with respect to that variable to infinity will give us the Laplace of a function of t divided by t. So what we are going to be proving is the integral coming from this variable, which is equal to s. Now this variable can represent it another letter, it can be m or n, but is equal to s to infinity of a function of this variable with respect to this variable will be equal to the Laplace of a function of t divided by t. Now to prove this, since now we all know that the integral coming from 0 to infinity of exponential minus st function of t, the t is equal to, we eventually give the answer we get will eventually give us a function of s, right? So that means when I take out this function of this variable, for example, let me take out the function of this variable and express this, since this function of s here is equal to this. Now let me express this to be equal to this also. So if I express this to be equal to this will be giving me coming from 0 to infinity exponential. Now instead of me writing s here, alright, I'll represent it as what? This variable. So this is minus this variable t of a function of t dt. Right? So now this function of this variable, I've expressed it as the normal Laplace expression. So now instead of me writing this, I'll substitute it inside this. Substituting this in this, we'll be having integral coming from this variable, which is equal to s to infinity. Substituting this to this will be giving me integral 0 to infinity exponential minus that variable function of t with respect to t, right? And don't forget what this variable dt. So now let me just call this variable the unknown variable, right? We just brought it in for us to be able to prove. You can represent it with m or n or any letter of your choice. I just choose to represent it like this. So now what we have, since I've successfully substituted this into this, now let's prove that to give us the Laplace of a function of t divided by t. Now then we can solve questions. So now for us to solve this, right, we're having double integral. So now for us to solve it, you have to solve the first integral with respect to a particular variable and the second integral with respect to another separate variable. So what am I trying to say is that to make it easier for us to integrate, since we're having this variable with respect to infinity and we're having this variable here, let's bring this variable together. To bring this variable together, we'll be having, taking this one at the back, we'll be having, this is integral coming from 0 to infinity, right? And this is integral, this variable which is equal to s of infinity exponential minus this variable. Why I'm bringing this variable to, instead of this integral from 0 to infinity, I want to integrate it with respect to this variable. It's because with respect to this integral is because of this variable. Now this variable can be found in this exponential here. So it's very easy for us to integrate it with this exponential, integrate this with respect to this. So that's why I'm bringing this with respect to this with respect to this. So taking this one at the back of this is what we'll have. So bringing the integral here, then exponential minus this function of t with respect to this variable and with respect to t. So we are going to be using this integral to integrate this and using this integral to integrate this. So now let's proceed. So like I said, we're going to integrate this with respect to this and integrate this with respect to this. Integrating this with respect to this, we're having double integral. We're going to be differentiating it with respect to two different variables. So this we are going to be integrating this with respect to this. So integrating this with respect to this, right? So what I'm going to have is, since I'm integrating with respect to this variable here, I don't need this function of t. This function of t I write it as a constant, right? Taking this function of t at the back of the integral sign, this we are having function of t integral this, which is equal to s to infinity exponential minus this with respect to this, right? So integrating exponential minus this variable times t, we'll be having function of t, which will be open bracket exponential minus this divided by minus t, right? Because I'm integrating exponential minus this variable times t, so integrating this will be having integrating this. Remember, integrating exponential is going to be divided by the coefficient of that variable. So divided by minus t, right? So this will be this is what we'll be having. Then don't forget our limit from this variable to infinity, right? So this is equals to s to infinity, right? So now this is what I'm going to be having. So I'm going to be applying my definite integral. So I'm going to be applying what we call my definite integral. So definite integral from this limit to this limit. So applying this to this, right? So if I impute infinity into this, I'm going to be having 0, right? So infinity, that means exponential of infinity. That means anywhere I see this variable, I'm going to put infinity. So anywhere I see this variable, I'm going to put infinity. So putting infinity into this, exponential of infinity is 0, right? So I'm going to be having function of t open bracket exponential of minus infinity times t divided by minus t, and minus, putting this into this, will be having exponential minus st divided by minus t, right? So exponential of infinity is 0, right? So we'll be having function of t, so we'll be having equal to function of t open bracket 0 minus exponential minus st divided by minus t. So this is what I'm having. So when I apply my definite integral, putting infinity into this gives me 0, minus putting s into this. Remember, this, I said this variable is equal to s. Putting s into this, and this is what I'm having, right? Now let's continue. So multiplying through by function of t, right? Continuing from where we stop, multiplying through by function of t, this time this is 0 and this time this will be having, now minus times minus is plus, right? So this time this will be having function of t exponential minus st divided by t, right? So having solved this, we are left with this and we are left with this. So bringing this down, this is integral coming from 0 to infinity, right, with respect to t, right? So now we all know that our normal representation for Laplace transformation is the integral coming from 0 to infinity of exponential minus st function of t dt. What am I trying to say is that, if you can remember our last video, I said I gave a general Laplace expression, which is the Laplace of a function of t is equal to integral coming from 0 to infinity of exponential minus st, which is function of times function of t dt, right? This is our general expression for Laplace transformation. So having this, because we can actually see this in this, then divided by t. So this means that the integral coming from 0 to infinity of function of t exponential minus st dt, we can substitute this as the Laplace of the function of t. So substituting this divided by t for the Laplace of function of t, because Laplace of function of t is the integral coming from 0 to infinity of exponential minus st a function of t dt. Remember, which is also equal to a function of s, right? But we don't need this. This is what we need, because this we can actually see in this part. So substituting this to this, will be having Laplace of the function of t divided by t. So we have successfully proven that the Laplace of a function of t divided by t. So we have successfully proven that the integral coming from that variable to infinity, the function of that variable with respect to that variable, will be equal to the Laplace of a function of t divided by t. You can remember what we actually started proving from. So we have successfully proven that. So now let's take an example. So having proven that the integral coming from 0 to infinity, so coming from this variable which is equal to s to infinity of a function of this variable with respect to this variable is equal to the Laplace of the function of t divided by t. Now this is basically all what the theorem 3 is trying to tell us, that when we have the Laplace of a function of t divided by t, we can relate it to this, the integral coming from this variable to infinity of this variable with respect to this variable. Now you might not understand what I'm trying to say exactly, but I'm sure you will understand when we take an example. So that is not the only condition for this theorem 3. So theorem 3 will be valid, that is, this will be valid if or provided that the limit of a function of t divided by t when t tends to 0 exists. So this is another condition for our third theorem of Laplace transformation. So we can basically state this theorem that the Laplace of a function of t divided by t will be equal to the integral coming from this variable to infinity of a function of this variable. Now this variable is, you just added an extra variable, but you don't actually know why they added it, because you don't actually need it. All you just need, you can, like I said, you can represent it by another letter. It can be m, can be n, can be n, it can be m, or you can be n, any letter you wish, but the m on this integral is equal to s. So, like I said, the Laplace of the function of t divided by t will be equal to this, provided that the limit of the function of t you are given divided by t exists. So now let's take an example. So the example we are going to be taking is find the Laplace of sine 3t divided by t. So this is the example we are going to be working with, right? So now, before we proceed, like I said, this will become valid unless this is carried out. That means before we start solving a Laplace question in which the function of t is being divided by that same function of t, in which the function of t is being divided by t, we will first note that we must carry out, or we must check if the limit when t tends to 0 of the function of this function of t divided by t exists. Now if it exists, then you proceed to checking or to solving it. If it doesn't, you can't actually solve it. So now let's check if this limit exists. So we're going to be checking if the limit of sine 3t divided by t when t tends to 0 exists. Now this is our first step. So now to check if this limit exists, right? So now when t tends to 0, so if I put 0 in this and 0 in this, I'm going to be having 0 and 0, right? 0, replace t with 0. This is 3 times 0, which is 0. That's sine 0, and sine 0 is also the same thing as what? 0, right? And this is 0 here, and we have also 0. So this is an indeterminate answer, right? This is an indeterminate answer. So what we need to do right now is to apply L'Hopital's rule. So we're going to be applying L'Hopital's rule. Right? So applying L'Hopital's rule to this, right? We are going to be differentiating each function individually. So differentiating sine 3t, what am I going to be having? I'm going to be having cos, that's 3 cos 3t, right? Differentiating t, I'm going to be having 1, right? So I'm going to be having 1. So this is the limit when t tends to 0 of cos of 3 cos 3t, right? So solving this limit, right? Because I've applied L'Hopital's rule, because differentiating this, I have 3 cos 3t, and differentiating t, I have 1, right? So this is divided by 1. So applying this, right, taking the limits when t tends to 0, this is 3 cos 0, right? 3 times 0 is 0, right? So cos 0 is 1, right? And this gives me equal to what? 3. And 3 is a definite value or definite number. So that means the limit of the function of t divided by t exists. So as long as the limit exists, I can apply this theorem. So now let's proceed. So we've successfully carried out our first step by proving that the limit of this and this exists. So our second step, we find the Laplace of the function of t here. So if you compare, like, okay, what's the function of t when looking at this? The function of t here is sine 3t. How do we know? When we compare it to the Laplace, because the rule says the Laplace of the function of t divided by t, right? So compare it to this, the function of t is sine 3t. So we're going to be taking the Laplace of sine 3t. The second step now is to take the Laplace of the function of t. So taking the Laplace of sine 3t. You all know that the Laplace of sine 3t is very easy, because I taught it based on our last video. We actually have to prove the answer to the Laplace of a sine function. So the Laplace of sine 3t, we all know that is 3 divided by s squared plus 9, right? This is the Laplace of sine 3t. So I've gotten the Laplace of the function of t, which is sine 3t. So now what do I do next? Now the rule says the Laplace of function of t divided by t is going to be the integral coming from this variable, which is equal to s to infinity, of the function of this variable with respect to this variable, right? So now, meaning that the answer I get, which is the Laplace of function of t. Now, remember this is terms of function of s, right? So meaning that the answer I get, I will represent this function of s in terms of this variable here and integrate it. As simple as that. So since my function of s, the function of s I'm having is 3 divided by s squared plus 9. Now this is my second stage. This is my second step. So since the function of s is 3 divided by s squared plus 9, what will be my function of this variable? The function of this variable here will be 3 divided by this variable square plus 9, just like replacing s with this variable. So since I have this variable, what do I need to do is to put it back here and integrate it. So substituting this now in this, we'll be having integral this variable, which is equal to s to infinity. Substituting this for this, right? Because we have actually expressed this to be in terms of this, right? So putting this here, we'll be having 3 divided by this square plus 9 with respect to this. So what we're going to do now to get our final answer is to solve this. So when we solve this, we have our final answer, and that is that. So now let's proceed. So we're going to be simplifying out solving this, right? So now I'm integrating this with respect to this, applying our limits. So before we apply our limits, we have to integrate it first. So integrating this, will be having integral 3 divided by this variable plus 9, right? With respect to this. Now this is a very simple integral question, right? This is a very, very simple integral question. So for us to integrate this, instead of me going through the long step, we all know that the integral of z of 1 divided by z squared plus a squared, integrating with respect to z, is equal to tan inverse of z over a. Now this is a rule in solving this kind of integral question. The rule says the integral of 1 divided by z squared plus a squared, a which is a constant because we are integrating with respect to z which is a variable, is equal to the tan inverse of z over a. So we are going to be applying this rule in solving this integral question. So solving this integral question, since 3 is a constant, take the back of the integral sign. So this is 3 integral 1 divided by this plus 9. So solving this integral question, we'll be having tan inverse of z, which is my variable, but in this case now, this is my variable, right? So we'll be having this over a here is a constant. So if I compare this to this, the a I'm going to be having here, the a square I'm having here is 9, right? So comparing this to this, my a is 3. So this will be having 3, right? So now this is my answer. So since it's constant here, multiplying through by this, will be having 3 tan inverse of this variable divided by 3. Don't forget our definite limit, which is from this variable we are having here, will be going from equal to s to infinity. So we're going to apply our definite limit. So applying it, right? So now I'm going to be substituting the infinity into this and substituting s into this, right? Anyway, I see this, I'm going to put s. So I'm substituting this in this, so we're having taking 3 to the back. So this is 3 open bracket tan inverse of, now anyway I see this, I put infinity, right? So this is infinity divided by 3. Infinity divided by 3, you all know that is also is infinity, right? Infinity divided by any number is infinity. So minus tan inverse of s over 3, right? Close my bracket. So tan inverse of infinity divided by 3 is infinity, right? So this is 3 open bracket tan inverse of infinity minus tan inverse of s over 3. So tan inverse of infinity, right? You all know that is 90 because tan 90 gives me infinity. So tan inverse of infinity is 90. So but 90 in radian form is what? Pi over 2, right? So this is 3 open bracket 90, right? Tan inverse of this is 90, and 90 in radian form is pi over 2. So we'll be having pi over 2, right? Minus tan s over 3, right? So multiplying through by my 3, we'll be having 3 pi over 2 minus 3 tan inverse of s over 3. So this is my final answer to the Laplace of sine 3t divided by t is equal to 3 pi over 2 minus 3 tan inverse of s over 3. So thank you guys for watching, and please subscribe.